Welcome everyone to today's statistics seminar. It's my great pleasure to introduce Lihua Lei from Stanford University. Lihua got his PhD from Berkeley, working with under the supervision of Peter Bickel and Michael Jordan. And now currently he's a postdoc researcher in Stanford working with Emmanuel Candace. And today he's going to talk about very exciting topic about conformal inference and statistics. And before I pass to Lihua, I just like to remind you that the audience that if you have questions, you have three ways you can ask the question. The first one, you can type your question in the chat. And the second one is that you can type your question in the Q&A section, or you can just raise your hand and I will allow you to speak. And without further ado, Lihua, time is yours.
Thanks for the kind introduction. And it's my great pleasure to be here to share some of my recent work. So as you can notice here, I changed the title a little bit just to make it more inviting, because the previous one is a little bit dry, but the contents are the same. And also, I would like to make this talk as interactive as possible. So if you have any questions, just feel free to interrupt me or put that into Q&A. And I will also take quite a few pause for questions. So this talk is about what can conformal inference offer to statistics. And hopefully, in the end, I can give you some answers to this question. And nowadays, we're deploying machine learning models in many applications. And these applications often involve high-stakes decision-making, like self-driving cars, disease diagnosis. And as a statistician, a central question for me to ask is that, can we have reliable uncertainty quantification in these predictions? So one big challenge is that, unlike the old days where we focused on linear models or generalized linear models, today's predicted algorithms are super complicated, like random forest, gradient boosting, neural networks. So they're complicated not just in terms of their architecture, but also in terms of their pre-processing process, or their tuning procedure, or the tons of engineering tricks that make these models really work, make these algorithms really work. So although currently there has been a lot of great effort trying to opening up this black box and see why they work well, and whether we can have theory to guide this, to guide the changes of this algorithm. But at this moment, there's still a huge gap between theory and practice. So usually, in order to analyze these algorithms, you have to greatly simplify the algorithms and also the data generating process. So here, we want to do something different. So we want to take these current practices, because they have already shown to be very effective, but we still want to build uncertainty. So fortunately, we have something called conformal inference. And roughly speaking, conformal inference will take any predictive algorithm that produce a point estimate of certain kind, and then it will wrap around this and pass that into a protection layer, turning it into a trustable interval estimate. So more concretely, this conformal inference is going to take IID training samples, X and Y, where X is the covariate or features, and Y is the outcome of interest. And then for a new test point, whose Y has yet to be observed, conformal inference is able to construct a predictive interval C hat, which is covariate dependent, such that the probability that the C hat evaluated on a new sample would cover the outcome Y with probability 90%. So what's amazing about this framework is that this guarantee holds in finite samples for any distribution of X and Y and for any predictive algorithm. So this echoes my point made in the last slide, that here we don't need to change our algorithm. We don't need to simplify that. And we don't need to simplify the data generating process, because this guarantee holds without those assumptions. And for those who have heard about conformal inference, I know you must have questions like, oh, what about conditional coverage? What about type 2 error? What about tightness? Later on, I will touch upon that in my context. But the issue I want to point out about conformal inference is not about the guarantee or the other theoretical properties, but really is that conformal inference implicitly assumes that our outcome is observed for every training sample. So in other words, this is really about predicting, and it's about predicting the same. But in statistics, we have a lot more applications which have much more complicated structure than this. So for example, we have counterfactual inference. And counterfactual is a concept that has been widely studied in causal inference, reinforcement learning, algorithm fairness, and so on. And roughly speaking, it measures what would have been one's response had one taken the treatment. So by definition, it is only observable for those in a particular treatment arm. So it's partially observable. And another important example is the time to event outcome, which is widely studied in survival analysis, industrial life testing, economics, and so on. And this type of outcome is usually censored by study termination or lost to follow-up. And again, it is only observable for those whose event has already occurred. So in this talk, our goal is to construct calibrated prediction intervals for partially observed outcomes. Now, let me start with the first part, which is the conformalized counterfactual inference. And this part is a joint work with my postdoc advisor, Emmanuel Cantus. So as you may know, counterfactual is a very philosophical concept. And in order to talk about that, there are many frameworks which allow us to talk about that. And here in this talk, I will stick with the potential outcome framework because I consider a very simple setting where there's binary treatment and there are covariates. And of course, there are many other frameworks like causal diagrams or invariant prediction. Turns out, at least for some of them, our method still works. But just for simplicity, I will stick with the potential outcome framework in this talk. So the potential outcome framework can be illustrated by this science table. So let's say we have 10 units, 5 treated and 5 control. And then we can observe all their covariates, pre-treatment covariates. And we can observe their treatment assignment. And for each of them, we assume that we have a pair of potential outcomes, Y1 and Y0, which measure what would have been this person's response had she been assigned into the treated or control. And then we assume that the observed outcome equals to Y1 if it is in the treated, otherwise equal to Y0. So you can see that once we write this down, we have already assumed something. So for example, this observed outcome doesn't depend on other people's treatment assignment. So in the literature, this is called pseudo. And this excludes things like interference. So for example, if you have a network where people can affect their friends, then there will be some spillover effect. And in that case, you cannot write the potential outcome in this way. But here, we will focus on the simpler setting. On top of this assumption, we will assume 2 more. And the first one is called Superpopulation Assumption, which assumes that this quadruple xi, ti, y1, y0 are IID across units. And the last one is called unconfoundedness, which essentially assumes that given any value of covariates, we have a completely randomized experiment. So I want to emphasize that all these 3 assumptions are pretty strong, but meanwhile, they're pretty standard. And in this talk, I will stick with the 3 assumptions because this is a starting point. But there has already been some effort in relaxing each of them. So for example, people are looking at the case where this unconfoundedness is wrong, but then doing sensitivity analysis. And also, there has been some effort in relaxing the superpopulation assumption. I'm not aware of any existing effort relaxing this, but I believe there will be. So here, just keep in mind that the 3 assumptions are standard and strong, but let's just stick with that and to take this work as a starting point. So once we set up this, now we can define our goal. So our goal is to find an interval estimate, which is covariate dependent, that covers the potential outcome Y1 for a control unit with probability 90%. So here you see that we have a conditional event that this person is in the control. So it's actually not essential. And I wrote it here just to motivate problem, because for control units, Y1 is the missing counterfactual. So that's illustrate why we call this counterfactual analysis. But in our paper, we have different criteria, like you can remove this, or you can consider settings like generalization, but I won't talk about that. So I'm happy to talk about that offline. And one more thing about this criterion is that this may look like a confidence interval, but it's not quite, because here our inferential target is a random variable, it's the outcome. So in the statistical literature, this is called prediction interval, and it is not the same as confidence interval. And for example, this prediction interval is not going to shrink to a point, even in infinite samples, unless your Y1 is a deterministic function of X. Okay. So that's something you can keep in mind. So now before going to our method, let me briefly review the data generation process of an observational study under this setting. So here, let's say we have 10 people, and each of them has a propensity score. And then for each of them, we will toss a coin to decide whether to put them into the treated group or control group. And under SUTVA, we know that for the treated units, Y1 are their observed outcomes, and Y0 are their missing counterfactual. And then for control units, Y0 are their observed outcomes, and Y1 are their missing counterfactuals. So now our goal becomes to make inference on this pink icon for this blue one. Or in other words, we want to infer Y1 of this control units. So a naive idea is just to use the observed treated units as the study population, because that's the population where Y1 is available. And then try to learn something from there and generalize your finding into this hidden population. But there's a problem, which is the distribution mismatch. So it turns out that under the unconformance assumption, we can show that the joint distribution of X and Y1 can be decomposed in this way in both populations. So it turns out the conditional distribution of Y1 given X is the same. So that's good, because that means these two populations do share something. And otherwise, it's hopeless to make inference from something completely different. But what distinguishes them is the covariate distribution. And you see that by definition, this is the treated group. So the covariate distribution is X given that this person is in the treated. But this one is the control group. So the covariate distribution is X given this person is in the control group. So here's the illustration. In the left column, I made the real world plots. In the right column, I made the counterfactual world plots. And in the top row, I give the scatter plot of Y1 versus X. You can see that these two plots look very different. But the unconformance assumption makes sure that for each slice of X, the Y distribution is the same. So the entire difference between these two plots is driven by the covariance shift. And now we can rephrase our goal as using IID samples from one distribution to construct prediction interval for another distribution. And here in particular, the covariance shift, which is defined as the likelihood ratio or density ratio, is proportional to 1 minus the propensity score divided by the propensity score. So if you have been working in causal inference, sorry, this is pretty standard. This is pretty standard IPW type weight. But if you haven't worked in this area, that's totally fine. The only takeaway message from this formula is that the covariance shift is entirely driven by the selection process, which is measured by the propensity score. So this is pretty much about the causal background of this talk. Let me take a pause here. So I do see a question in Q&A. So the question, I can.
I can spell that for you. So,
okay, great. Yeah.
The question is that I'm confused about why distribution of covariate X depends on T.
Oh yeah, that's a great question. So here you see that in general, we are not assuming we have a completely randomized experiment. So if that's the case, then the distribution of X doesn't depend on T. But in general, you see that this observed treaty units are sampled from the treaty group. So by definition, the joint distribution of X and Y1 will be conditioning on T equals to 1. So then you can decompose that as this term times the probability of Y1 given both X and T equals to 1. And unconformance assumption removes that T equals to 1 here. But this part still remains, right? So for example, if there's some selection process which make like the people from West Coast much easier to get access to, then you will see that given the treatment group, so in the treatment group, the West Coast people will be overrepresented. So that's why the covariate distribution will depend on T. So does that answer the question?
Yeah, I think that should answer the question. Okay.
Okay.
So, yeah. If matter how. Okay. Yeah. So yes, that answered the question.
Great. Yeah. So is there any question? I can take a pause here. Okay. So if there's no more question, now I'm going to move on to the next part, which is our actual meat, the conformal inference. So as I mentioned before, the standard conformal inference can only handle the case without covariate shift or without distributional shift. But here we have a covariate shift. Unfortunately, we have a variant of conformal inference called weighty conformal inference, proposed 2 years ago by Tibshani, Babar, Candice, and Ramdas. So this framework, roughly speaking, takes IID samples as input. Then as long as the covariate shift is known, it can wrap around any predictive algorithm and generate prediction intervals that is calibrated under the new distribution. So in this talk, I'm going to illustrate one instantiation of this method, which we are using, called weighted split conformalized quantum regression. And let me start illustrating that. So this method will start randomly splitting the data, the observed treaty units, into two folds, a proper training set and a calibration set. On the training set, you apply your favorite quantum regression method to try to estimate the 5th and 95th quantile of Y1 given X. So here, you can use linear quantum regression, you can use quantum random forest, you can use quantum neural net. Or if you are a Bayesian, you can feature a Bayesian model and then use the posterior quantile as the estimate. So anything is fine. And then you get these two black curves, and you apply that onto the calibration set. Then for each point in the calibration set, you calculate something called Sine Distance, which is the distance between each point to one of these two envelopes, which is closer, multiplied by a +1 if it is outside the range, or a -1 if it is inside. So here's the formula for that, but the formula itself is not important. So the only thing important here is that we define a score called Sine Distance. And it's roughly speaking, it's a distance, okay? And suppose we have 1,000 points in the calibration set, then we have 1,000 Sine distances. And we can collect all of them to get a histogram. The standard conformal inference would directly operate on this histogram. But here, we need one extra step, which is the reweighting step, in order to account for the covariate shift. So just for illustration purpose, let's say we have this one-dimensional X, and let's say the covariate shift is monotonially increasing in X. Then what we are going to do is we will shift the mass to the places where the covariate shift is large. So here, in this case, we know that we need to shift the mass to the right. So after certain reweighting, you can see that this red histogram is kind of going to the right. And that ends up with this blue histogram. So mathematically, the reweighting scheme is super simple. It's just for each sine distance, you calculate the covariance shift and normalize it. So in other words, it's proportional to the covariance shift. And if the covariance shift is null, that means this weight is null. And otherwise, you can estimate it, and at least you get an estimated reweighting scheme. And that gives you a blue histogram. And once we got this, we take the 90th percentile of this blue histogram and call that QX. And finally, we output the interval as this 2 quantile estimate plus and minus QX. Okay, so that's the procedure. The procedure is super simple and can wrap around any quantile estimate. In order to get a better sense of what this procedure is doing, let's stare at this interval for a bit. So without this QX, this interval is just a raw interval. It's the interval given by the raw quantile estimate. So if we can consistently estimate the conditional quantiles, we don't need to add this actual term QX, because that's already give us 90% quantile. Sorry, 90% coverage, because 95 minus 5 equals 90. But that's not often what we observe in practice, especially when we apply complicated algorithms. So in many cases, we observe that those algorithms tend to be overconfident in the sense that the 5th percentile is actually estimating the 15th, while 95th is estimating 85th. So without this QX, we would wind up with a 70% coverage, and that's too bad. And so essentially, this QX is a calibration term that saves you from this overconfidence. But meanwhile, if you happen to get an algorithm that conservatively estimates this quantiles, then it can save you from conservativeness. So essentially, this QX, this conformal inference, is recalibrating what you already have at hand. So that's the procedure. And it's perhaps the most important part in this talk. So let me take a pause again to see if there's anything unclear.
Okay, I think somebody raised okay, there are 2 hands raised. So I think the first one is Carlos. Let me allow Carlos to ask.
Yeah, please.
Carlos,
Hi, Carlos.
Hi, can you hear me?
Yeah, I can. Hi.
Oh, thanks. So that's great. So this is just a clarification question. So the estimate, like our target of inference here would be the quantile of the counterfactual distribution. Is that correct?
Not really.
No?
So you see that this is not an estimation problem. So our goal is just to get this prediction interval. And if you can get the conditional quantile, of course, you can get this prediction interval, but not vice versa. So it's like you may get this prediction interval without targeting on certain quantile. So for example, I don't want to make things too confusing, but suppose here, instead of fitting 5th and 95th, you fit like 8th and 92nd, then you can still have valid coverage. So that's not the case where you want to estimate the 5th and 95th percentile. So okay, does that make sense?
Yes, but that quantity that you have, so the adjustment that you're making, so let's take the lower limit, Q hat minus big Q, right?
Yeah.
So can we say that that is targeting any property of the distribution?
Yeah, so for this part,
yeah,
I will show you the formal results in the next few slides, but roughly speaking, what we can show is if you can correctly estimate this or accurately estimate this, as most of us did in the classical statistics, then this is targeting on the true conditional quantile. Okay. But what's more about that is even if you completely misspecify your model where your estimate is inconsistent or even divergent, then this interval still gives you the valid coverage. It's just that we cannot interpret this as a quantile estimate, as a good quantile estimate.
Okay, great. If I have further questions, I'll ask later. Let me
Yeah.
give to the other person.
Yeah, thanks.
Thank you.
So I see Alex has another question.
Okay, yeah. So Alex's question is that I may have missed something, but why do we look at 5% of 95% quantile and not at any pairs of quantiles with 90% difference 90%? And
that's
then,
sorry.
I think that wise then we can optimize it to choose the shortest interval with 90% coverage.
Yeah, that's a great question. So I'll also touch upon that point in the next 2 slides. So just long story short, here, this is just for illustration, okay, because 5 and 95 is like the most natural choice. But you could definitely optimize over that. Like you can choose between 191, 292, and 595. Although this is not the focus of this paper, but I will talk more about that. And on the other hand, if you can consistently estimate your contextual quantile, there's a practical problem. Like if you give the 1 and 91 and you hand it to the practitioner without telling them that this is 191, then usually the practitioner would like to interpret it as a symmetric interval. And that can make some confusion. So I think, yeah, so the short answer is this can be much more general, but in practice, in some cases, we may still want to produce this symmetric one, just to avoid confusion.
Okay, so finally, Thomas also have a question, so let me allow Thomas to ask.
Yeah, please.
Yeah, so this is a really basic question, but on the right-hand side, where you've got the density plot, so is there going to be a plot like that for every value of x?
Yeah, okay, so this is a great question. So because this is a subtle part, which I haven't dig into detail. So you see that the reason this thing depends on x. So are you asking that why this qx depends on x?
Precisely, yes, yeah. Yes.
So that's because you see there's a term. So x only appears here. So in the case without covariance shift, this term is just a constant, 1 over n plus 1. That's why in standard conformal inference, this calibration term is a fixed quantity. It doesn't depend on x. And in most of the cases, this term doesn't really matter unless this wx is really large. So the case where wx is large is the case where this covariance shift is huge, right? So that means your test point is so different from your training point. And only then this x would play a role here. Otherwise, you see that there are n terms here and only one term involves x. So it's almost the same as 1 over n plus 1. And you wouldn't, so the dependence of qx on x is really minor in most cases, except in the case without overlap. Does that make sense?
Yeah, just so I understand, so the histogram you're showing us is the conformity scores for all the data, but then you're reweighting it based on just the specific x data point. Is that right? Or is,
that's right.
Okay.
Exactly.
Okay, got it. Okay, thank you.
Yeah. So the sign distances are the same. It's just the reweighting scheme is a little bit different.
Got it.
Great. Yeah.
Okay, great, thanks. And we have a final question from the meta. And so the question is that qx is the 90% quantile of the conformal score. And firstly, why is widening the quantile interval a good idea? And secondly, does it lead to any kind of overcompensation?
Oh yeah. Again, good question here. So here, qx doesn't have to be positive. So we're not necessarily widen the interval. As I mentioned, if we happen to be conservative in the sense that the 5th estimate, say, the 2nd, and the 95th estimate the 98th, then without calibration, we would be conservative. But this qx can be negative in that case. So yeah, that answers the first part of your question. And I guess that's also allude to your second question. Like this is, so what we will show is if you can consistently estimate the quantile, then this term is approximately 0. Maybe in the next slide, I can exactly answer your question. Yeah.
Okay, great. I think that's all the questions. So.
Great. Okay, now I can move to the theoretical guarantee. Yeah, thank you all for the questions. So the first one is probably related to the question, which is, suppose we have randomized experiment, in which case we know the propensity score. So then we can directly plug in the true propensity score in this procedure. So then what we can show is, first, this coverage is always above 90% without actual assumption. By that, I mean any assumption other than the suitable IID and unconformedness. So this is very similar to standard conformal inference in the sense that this guarantee holds for any conditional distribution, any sample size, and any procedure to fit conditional quantiles. But then the other part is about whether we overcompensate for this. So are we going to be too conservative? So it turns out, under two other mild conditions, which are that the sign distances are almost surely distinct, and we have some overlap condition, meaning that everybody has a positive chance to go into the treated and control groups. Then we can show that this coverage is upper bounded by 90% plus a constant divided by n, where this constant only depends on overlap and is universal across the three stuff. So I think this partly answers the question because we're not overcompensated and the coverage is pretty tight around 90% unless you have bad overlap. But you know that if we have bad overlap, then barely any method can work because the only thing we can do is we assume extrapolation. So we assume that we have a good outcome model and we extrapolate. Otherwise, a bad overlap means that at some places, there are no treated units. There are no people exposed to the treatment. So that means that the potential outcome is barely identifiable. But here is that under the standard overlap condition, we can show the coverage is pretty tight. So that's the first part. And the second part is about observational study. So suppose we don't know the propensity score, and then we can estimate it. And once we plug in the estimated version, then informally, we can show that the coverage is approximately 90% if either the propensity score or the conditional quantiles are well estimated. So here, I only present the informal version of this. If you're interested, I can show you the exact version, the rigorous version in the end. But I think the message is this, is that this result is pretty similar to double robustness for ATE, in the sense that we only need to know one of these two things, which are the treatment assignment mechanism and the outcome model. So this is good. This means we have more robustness. And if we happen to get the propensity score wrong, but if we can still get the outcome model correct, we still get this coverage. Okay. And on the other hand, if you get both wrong, basically you know nothing about data generating process, so that it's impossible to make any inference, any useful inference. But the next thing is, so that's pretty much about the type 1 error, about the coverage. But then we have to talk about the type 2 error or the tightness of the intervals or conditional coverage. So this is that slide I was alluding to at the beginning. So suppose we have good outcome modeling, meaning that we can consistently estimate those percentiles. Then what we can show is our interval will be approximately the oracle one, given by the 5th and 95th. And at the same time, we can show that the conditional coverage or the coverage given the covariate value X is approximately equal to 90% with high probability over the randomness of the covariate. So you see that a lot of people say conformal inference is only given marginal coverage and cannot give conditional coverage. That's a misunderstanding. And turns out, if you have good outcome modeling, you can achieve conditional coverage. And basically the reason you can achieve it is because your interval is approximately the raw interval. And the raw interval gives you the conditional coverage. And that's the reason. But then you might say, what if the model is misspecified? Then I would say, if your model is completely misspecified, conditional coverage is perhaps not well defined. Because how can you say conditional coverage even without a correctly specified function class? That's not something well studied in the history of statistics. Because usually when people talk about a complete misspecification, they often change the target, change the estimate. So here are a couple of points before I take another pause. So the first point is that for symmetric unimodel conditional distribution, 5th and 95th is the optimal. But in our paper, we show that it continue to hold if we replace that by any beta to beta plus 1 minus alpha, as long as this window has 1 minus alpha mass. And you may ask, how do you adaptively choose this? There are many ways to do that. For example, you can use your training data to do that. And also there's a recent paper by Romano and Cercia showing that you can also do this even more adaptively. So the point is, this is something that can be done. It's just like it's not in my illustration of our method. And the main point of this slide is that if you have good outcome modeling, you would end up with good intervals and conditional coverage. So I know that people might have questions here. Let me take another pause.
Any questions?
Okay, so if there's no questions, I'm going to move on to the numerical results. But before that, yeah, here's one more slide I want to highlight, which is once we get the counterfactual intervals, for a new person, we can generate the interval for y1 and y0. And then we can contrast these two intervals to construct an interval for ITE, which is defined as y1 minus y0. And I just want to convince you that this is doable. Although it might not be efficient, but it's doable. So for example, if you want to generate 90% interval for ITE for y1 minus y0, although we know the correlation structure between y1 and y0 is not unidentifiable because they're never going to be observed at the same time, but you can do Bonferroni. So what you can do is you generate 95% interval for y1 and 95% interval for y0. Then you know that with probability at least 90%, they're both correct. Then you can contrast these two intervals to get an interval for ITE. Okay. And in our paper, we talk about some other methods, but I'm not going to talk about in this talk. And another point I want to make in this slide is that usually when people talk about heterogeneous treatment effect, they talk about Kate, which is the conditional expectation of ITE. But here, we're looking at ITE as a random variable. So there's a lot of debate on which one is better for, it's a better definition for individual treatment effect. And I'm very happy to talk about that offline. I think there's a lot of philosophical thing behind this, which are very interesting. But the thing is, it is what it is. So our thing can be used to generate intervals for ITE, for this random variable. Okay, so now I'm going to show you some numerical results. But before that, I want to show that we have a package, which is called CF Causal, which is available to download from my GitHub. So nowadays, I think getting a good software is super important because otherwise nobody will use the method. And in this simulation, so usually when people show simulation, they want to show that the method is good, the method can confirm the theory. But here I want to show slightly more. So here is a simulation with a very simple data generating process, where here we have 100 covariates generated from a correlated Gaussian, and we set y0 to be always equal to 0, such that the inference of effect, treatment effect, is the same as inference of the counterfactual. And then we generate y1 as a conditional Gaussian variable with very smooth mean and heteroscedastic errors, but also very smooth error function. Oh, sorry, a very smooth standard deviation function. And finally, we generate the propensity score with sufficient overlap. So you may say this is oversimplified. And yes, that's exactly our point. Because on such a simple data generating process, we should expect every method to work. But unfortunately and surprisingly, that's not the case. And if you want to find a more complicated example, you can find one in our paper. But here, I just want to stick with this one. That's the actual message I want to convey here. So here we consider 6 methods. And 3 of them are super popular methods in the literature. They're BART, XLearner, and Causal Forest. So they are very good methods, not just in terms of their theory, their paper, but also they all have well-documented packages. So you can easily play with that. And people found that they are very good algorithms if the goal is to estimate Kate. So they produce very good point estimate of Kate. But here, we're going to do something else. So we're going to take their confidence intervals for Kate and evaluate the coverage. And apart from the 3 methods, I also include 3 of our methods, which wrap around the BART, quantile boosting, and quantile random forest. And here, this is the plot for the coverage of Kate, which I call a sanity check. And that's because our method is not designed to cover Kate. It's designed to cover Y1. But it's still valuable to show this plot because everybody else is looking at Kate. So surprisingly, we found that all these methods significantly undercover, even for such a simple data generation process. So you see that the coverage here is only 80% or 70% or 50%. And I would say all of this method have certain theoretical guarantee and certain optimality in some regimes. But it's just that the asymptotic doesn't kick in this problem. On the other hand, for our methods, you see that they are all conservative. And this is not ideal. So ideally, we want things to be exactly on this line. But in many applications, being conservative is better than being anti-conservative. So I'm not going to overemphasize this point, but this is like the observation. And some people might say, well, all these methods are pretty good, and we can find a tons of papers showing this method are good. But why is something different here? So the main point is that coverage is not the same concept as accuracy. So these 2 concepts are almost completely orthogonal. So you could have a very accurate estimator, but with very poor coverage for the intervals because you underestimate the standard error. Or you could have very poor accuracy because the parameter is only partially identifiable, but you could still have very good coverage. Okay. Oh, yeah, so Thomas has a question. What is sample size here? That's a great question. So the sample size here is about 500. So there are 500 units in the treaty group. So I think this is a pretty common scenario in practice. And we also try increasing the sample size, but things doesn't change so much. So you still observe this. And I think that's mainly because of some model misspecification issues. And I know like these 2 methods are non-parametric, but it's very hard to talk about what we mean by model misspecification in a non-parametric setting. But that's what we observed. And another question is how many covariates are relevant? So here, only 1 covariate is relevant. Sorry, for the mean, it's only 2 covariates are relevant. And for every other thing like propensity score and standard deviation, only 1 covariate matters. So it's a pretty simple one. Yeah. And the next one would be our actual mean, which is the marginal coverage of Y1. So in this case, you can see XLearner and Causal Forest undercover. But that's not a reason to criticize these 2 methods because they're not designed to cover Y1. So it's fine to undercover. And for BART, because it's a Bayesian method, so if we replace the credible interval by posterior predictive interval, it is supposed to cover Y1 as well. But still, it undercovers. And finally, for our methods, regardless of what method we are wrapping around, we see that at least the marginal coverage is right around this target level, as predicted by our theory. And the next one would be the average interval length. So here I plot this, I plot the oracle length as this blue line. Since here in this example, everything is symmetric and unimodal, so the optimal one is just the 5th and 95th. So we pretend that we know this and we give this oracle one. But then for all methods, we don't know that. We don't know the propensity score. We don't know the conditional quantiles, and we have to estimate all of them. So you see that here, the accelerometer and the causal forest have pretty short intervals, but that's only because they own the cover. And for BART, we know that it doesn't do a good job in this case. So you see that when we wrap around BART, the intervals are increasing a lot. So that's where the compensation kicks in which case we know somehow our method detects that BART is not doing a good job, and it has to compensate a lot in order to retain the coverage. But if you wrap around some other algorithms which are more robust to the heteroscedasticity, then we see that even with 500 samples, the interval length is pretty close to the oracle length. So it's just a proof of concept that this is something we should observe. Okay, so I see another question. So how did you undersmooth the causal forest estimator for the simulations? Yeah. So here we just use the default. And the point is, of course, you can tune this causal forest, tune this method in order to get a good coverage. So first, I think their default has already taken some of this coverage issues into account. But of course, you can tune this some in particular applications. But the point here is that we just want to show that if you don't tune that hard, you might run into a big trouble. And here, if you wrap around existing algorithm like quantum random forest, then you can always guarantee that. So your calibration procedure will tell you how much you need to expand or shrink. So that's pretty much about the numerical result and about the first part. So here's a brief summary about the first part. And in this part, we propose a conformal inference-based method for counterfactuals, which is reliable in the sense that for randomized experiment, it achieves a near exact coverage in finite sample with any black box. While for observational studies, it achieves a doubly robust guarantees of coverage. So maybe I can pause here for one quick question, if there is any. Okay, so now I can move to the second part. Don't worry about like the second part. Like the second part is pretty short. So this part is about survival analysis. And this is a joint work with Zhi Meiyuan and Emmanuel Candace. So the survival times are censored. And just to set up stage, I want to illustrate the censoring outcomes. And here we consider a setting cut type 1 censoring. And in this plot, we have 4 patients. And the horizontal axis marks the calendar time. And this vertical line gives the time of the day to do the data analysis. And you can conceptualize the start date as the date of confirmation for COVID-19. And today as the day that we run the data analysis. So of course, you can also use other start date, like date of symptom onset or date of severe symptoms. But here we just take this because our original motivation is for medical resource allocation. So using the date of confirmation makes a lot of sense in that setting. And here, this arrows marks the event time, the event. And for the first and third one, their events occur before today. But for the second one, we have yet to see the event. So as a convention, we use T to denote the survival time, which is the duration between the start date to the event time. And then use C to denote the censoring time, which is the duration between the start date and today. And in practice, we can only see their minimum, which is called censor survival time. So you see that for the second one, the censor outcome is strictly below the actual one. While for the third one, the censor one is equal to the actual one. So here, our goal is to fit in patient level data and pass that into a conformal wrapper to turn any model output into a lower confidence bound for the actual survival time, in the sense that it is below the actual survival time for a new patient with probability at least 90%. So here we only consider lower bound for two reasons. One is this is the right sensory setting. And if we don't make any assumption on the sensory mechanism, then the upper bound is essentially infinite. And another reason is in these applications, usually we want to have conservative risk assessment. We want to know a lower bound instead of an upper bound. So we take this both for a theoretical and a practical reasons. So the first thought of this is that, can we apply the same techniques as I introduced before by treating the survival times as counterfactuals? In particular, if we define an event indicator as whether this actual time is sensor or not, then we can see by definition, our observed sensor survival time would equal to the actual time if delta equal to 1 and C otherwise. So here a natural question is, can we treat T as a potential outcome under this quote unquote treatment delta? Turns out we can't, because in this case, the unconfoundedness is just too unrealistic. So here, if you read out the unconfoundedness assumption by using this notation, it means that T must be independent of the indicator of T less than C given X. But using a little bit of math, you can show that this almost never holds, unless in some very special corner cases. So in other words, if we take the observed quote unquote tricky group, it will have shift in both the covariate distribution and the conditional distribution. So we're not in the same scenario as what we had where we were before. So we cannot apply the weighty conformal inference. So that means we need something else. So it turns out what we are doing is the following. It's very simple. So here we first order the units by censoring time CI. That's why we need to assume a type 1 censoring setting. And then we choose a study population as the ones with a larger censoring time, where this threshold can be chosen via data splitting. And in our paper, we discuss how to choose it. But for the COVID setting, you can simply conceptualize this as 14 days. Okay, we just take everybody that has been test positive 14 days before today. And on this population, a crucial thing is we can define a surrogate outcome, which is the minimum of C now and the sensor outcome. And turns out on this population, this thing equals to T minimal C now. Okay. So this surrogate outcome is always observable because we can construct that using C now and our observed things. And then what we know is if we can construct a lower prediction bound for this surrogate outcome, it will be automatically a lower prediction bound for the actual survival time. So again, turns out if we compare this study population with our target population, we have the same structure, where here we have the study population with large censoring time, and here we have the target population without this actual conditioning, and they differ only in their covariate distribution. And turns out under three assumptions, which are IID assumption, conditional independent censoring assumption, which is pretty standard in survival analysis, and type 1 censoring, we can achieve finite sample validity if the censoring mechanism is known, meaning that we know the distribution of the censoring time conditioning on X. And also it has a double robustness in the sense that this is approximately valid if either the censoring mechanism or the conditional survival function is estimated well. So it has a similar flavor to the counterfactual inference. And for experts in survival analysis, you might find this type 1 censoring very annoying. And it is, because for COVID-19 setting, it holds. But for most clinical trials, it doesn't hold. And we have thought about this very hard. So in our paper, we had a very extensive discussion on why this is still useful beyond type 1 censoring setting. But I wouldn't get into that in this talk. So that's about the second part. And I see I have 3 more minutes. So I will just very quickly go through the next few slides, which is not super important. So as you can see, this conformal inference is super flexible. And it's definitely not limited to counterfactual inference and survival analysis. And there are a lot of uses. And it turns out we have works on election. We have works on outlier detection. We have works on risk-calibrated prediction in many computer vision problems like tumor detection, hierarchical classification, protein structure prediction, object detection, and many others. So I don't have time to go through this, but the point is this framework is very flexible and we can drastically generalize the idea to many other useful settings. So back to the title of this talk. What can conformal inference offer to statistics? And the answer is a lot. So you can see all of them share the same feature that if you fit in the data, and then you can wrap around black box and turn that into trustable results. So they all share the same theme that we can do valid inference under partial or even complete misspecification. So I will close this talk using a cliche quote. Well, we often say all models wrong, but some are useful. So this quote definitely has a lot of merit, but unfortunately, nowadays, it is often used to justify some bad statistical practice. Like people run their model, and they cross fingers and speak this for 3 times, and then everything works. So we just want to slightly shift this paradigm a bit by saying all models are wrong, but we can make them safe and useful. With that, I would like to thank you all for your attention.
Thank you, Lihua. It's really amazing talk. And any questions? Well, people might be gathering questions. So I personally, I'm actually quite interested when you mentioned that if we have either an E hat approximately EX and or a Q hat approximately Q, and then we have all these really nice results. So can you talk more about that? Because I was thinking that although in the paper, in the talk, you say they're approximately the same, but I guess if you know, let's say E hat minus E hat X minus E hat EX, like propensity score, you know the accuracy of that, I think you will be able to work out the coverage deficiencies, right?
Yeah, you are anticipating my backup slide. Yeah, so here is the exact result. And actually, we have an even more refined result showing the non-asymptotic rate. So here, roughly speaking, you see that here, this is a purely asymptotic, where if your E hat is consistent, or if your quantiles are consistent, then what you can show is you have this small O1 term, and you have this small OP1 term for the conditional coverage. But of course, if you have further the rate, like what's the rate for this? In our paper, we have a result for that, but it looks very messy, but I think it is just, I mean, conceptually, it's very easy to understand.
Great, thanks. And I see a question from Alex. Alex was asking, like, can you also say something about the efficiency of the conformal inference procedure?
Yeah, that's a great question. So you see that when we talk about efficiency, we often talk about the first order efficiency. So for example, if we have something to estimate, then the efficiency could mean that whether, say, it's min-max optimal in terms of convergence rate, or in the semi-parametric case, you mean that whether the variance is optimal, or like whether you achieve the semi-parametric efficiency. But actually, there's another important, okay, so you mean semi-parametric. So here, there's another level of efficiency involved in, which is even more important than the first order one. So the thing is, this is a case with 0 order efficiency. So if you go back to this, you see that even with infinite samples, your interval is not going to shrink to 0 or shrink to a point. So eventually what you are going to get is this plus a first order term and this plus a first order term. So the overall length is mainly driven by this, by the 0 order term. So in the 0 order sense, it is efficient. But in the first order sense, it is not. Or at least we haven't proved it's efficient. So as I mentioned in the last slide, in the back slide, we have some non-asymptotic result. So there, we're pretty sure that the result is not efficient in the classical sense. And also there's one more thing, which is you see that here we have two components. So it's even not easy to define what we mean by semi-parametric efficiency in this setting. But I think that's certainly an interesting question. And there has been some effort, including our work. But I think better is, so like defining the efficiency is the first step. So Alex, does that answer your question?
Okay, great. Any other questions? Personally, I have actually, I just saw a question coming from a Q&A, so it's from Fang. So is the Markov inequality giving zero order efficiency in inferring the normal mean?
It's Markov. No, I think it's different because if you have normal mean, you're in the estimation problem. So for estimation, there's no zero order efficiency because in infinite samples, you know what it is. So there's no, I mean, this problem is different from prediction interval. That's what I alluded to at the beginning, where prediction interval is fundamentally different from confidence interval. Yeah, but whether Markov inequality gives efficiency for that, I think it really depends on distribution. For normal, it definitely not, because Markov inequality is too loose. But maybe for a broad class of distributions, it is.
Okay. So personally, I actually have one question.
Please.
Can you comment more on like the individualized treatment like effect? Because I think that's actually, you can construct a prediction interval for that. But I think we all know that the notorious thing is that we never know how Y0 and Y1 are correlated. So
yeah,
that interval, I anticipate it could be very conservative in certain scenario, but it could be okay in certain scenario, I guess.
Yeah.
So probably you have the 90% coverage guarantee.
Yeah. So you see here that the thing is, the interval for IT is conservative, not because the procedures are conservative. It's really about our limited information about the correlation structure. So without further assumption, you can at best partially identify the correlation structure, but still, usually you have very low power without further assumption, like without assuming what the copular looks like. So in that case, it's like no matter what method you're using, you're going to be conservative. Because in practice, we may expect that in many cases, Y1 and Y0 are positively correlated, but you can never test it. So I think there are something that we can do, which is, and this is maybe some crazy thought. So suppose, let's say if Y1 and Y0 are multivariate Gaussian, then we could view their correlation as a sensitivity parameter. So now the question is, how can we incorporate this sensitivity parameter into our procedure? I think that's not easy because our framework is purely distribution free. And in that case, incorporating more information is not that easy. So, but I think if someone can figure this out, it could be useful in the sense that instead of generating one interval, we generate a sequence of intervals, one corresponding to a correlation measure. And in that case, maybe it's more informative to the practitioners. Because I know in econ, they do have some economic models which can give you some sense of what a correlation is. So if you combine these two things, you know where you should look at.
Okay, great. Yeah. And I think Carlos also have a question about when Qx is misspecified, but Ex is correct. Do you know what the lower limit and upper limit correspond to?
Yeah, this is a fantastic question. Yes, we do, but we know that in a very vague sense. Like, so, okay, so if I go back. So basically, the limit is very simple. Is that suppose, okay, so we need to distinguish two cases. The first one is if these two things are divergent, like they don't even converge to something, then we don't know what it is. Because in this case, I don't even know what limit means. But then I think what you are alluding to is, what if these two quantiles converge to something which are not the truth? So suppose like say 5th percentile converge to 15 and 95th converge to 85th. Then this Qx would converge to the quantity such that will converge to the constant such that this interval has the right coverage. Okay, so I mean, in some sense, this is trivial. Like because we have this tight 90% coverage. So the only thing that this QX can converge to is that thing. So theoretically, this thing does exist, but it doesn't have a closed form solution unless you tell me something about the conditional distribution. Yeah. So does that answer your question?
Great. And any other questions for Lihua? Okay, so
maybe I can add one more thing, because a lot of questions about this. So I think a high level point is, as a classical statistician, we are looking at the problems with correct specification or with misspecification, but we redefine the target such that this misspecification is not really misspecified. But in modern practice, complete misspecification is a common feature. And here you see a lot of odd thing is because we don't have a good understanding of completely misspecification, like how to define efficiency, how to define limiting behavior. I think this is all open, but I find it very appealing because this is one of the direction I really want to delve into. And I think it will be much better in the next few years. So I think Alex has one more comment. I guess your point is correct, only if the misspecific quantile is still a quantile function, no crossing of quantile curves. No, that's not necessarily. So you see that here we only care, our guarantee is only on the marginal coverage. So even if, let's say, for some x, it converges to the 7s, for some x, it converges to 8, but you can still find a constant such that after average over x, you get 90%. And that's where this QX will converge to. Okay, yeah. Okay, so I will stop here.
Okay, oh, finally, I think there's a Q. Okay, Thomas. Great talk. Okay, so if no other questions, then thanks Lihua again for this wonderful talk. And everyone have a nice weekend, and thank you all so much.
Thank you all for attending.
Thanks, Lihua. It's great talk.
Thank you.